Welcome to the fourth chapter of the lecture series. We are talking about damage modeling. My name is Dilek Güzel, and I am from the Institute of Mechanics at TU Dortmund University.
My name is Patrick Utzea, and while we have learned about the mechanisms and the characterization of damage, the focus will now be on deriving the correct models and their numerical implementation.
The fourth chapter will now deal with the modeling of damage. This implies that we will first have a short introduction into damage models at the advanced bachelor level, with a history and classification of damage, and with highlighting a well-known or common problem when we deal with the implementation in a simulation, namely the regularization of damage. Later, we will continue with some more sophisticated damage models on an advanced master's or PhD level. That is microscopic and macroscopic modeling, damage and electroconductivity, fatigue behavior, and finally, the optimization using damage predictions. Damage models can be classified briefly into brittle damage models and ductile damage models. This is a distinction you find very often in the context of continuum mechanics, while the terms brittle and ductile may be interpreted differently in other research areas. So please be aware that these terms may have different meanings in different scientific fields. Brittle damage models, for example, used for glass, affect mainly elasticity and are usually associated with elastic energy. You find that one of the first concepts is that of fracture energy that you find here, developed by Griffith as one of the first. It was not typically named damage, but it's associated with the energy that you need to create fracture. And other developments have been the scalar integrity variable that is in most cases defined as 1 minus damage, or damage is 1 minus B, where B is the integrity. And from the computational point of view, we have the development of phase field models for fracture, for instance, where we have the transition from the governing equations that we set up to really describe damage as a model to using the model and solving the equations numerically. So these theoretical components and the numerical component, they go hand in hand, and that they are of course based on the third component, which is experiments, as we have already seen in the previous chapters. While these brittle damage models are associated typically with elasticity, we have ductile damage models. Ductile damage models are associated with plasticity. That is, if you apply a deformation and maybe a load and you take it back, then you have some remaining deformation. And this is first, or has been first, related to the growth of voids in early descriptions, then also to the nucleation and growth of voids, and finally also found an extension to a very famous GTN model. You also have the effect that ductile damage, for example, in steel, affects not only plasticity, but also elasticity. For example, the degradation of Young's modulus. So the damage evolution might be coupled to the evolution of plasticity, while you then also change the elastic moduli as damage evolves. And there have been then some illustrative strain and stress-based damage models later on to relate that not only on the level of maybe voids, but later also on stresses, strains, and energies. And all these names and years you see here shall be representative, but of course not a complete overview. That's impossible to give here, such that we added some other literature references here as well. And also every work you find here has much more details inside on damage descriptions, on other ideas, but we wanted to give you here a first view on the basic ideas. So we have the distinction between brittle and ductile damage models. On the left side, we have elasticity, so you don't see a remaining deformation afterwards, like in fracture, for example, in glass or at low temperatures of steel, while in ductile damage models, you have plastic deformation, like steel at room temperature, for instance. Then these are some key variables you may find in this talk, on this presentation, and also in other lectures or books. Damage shall be described by D. Integrity is 1 minus D here. We have strains epsilon, stress is sigma. Plastic contributions are usually denoted by the index P. The yield function that indicates the onset of plastic flow is phi. The Helmholtz free energy psi here is very often used for models in the continuum mechanics community because that energy has some mathematical advantages for the descriptions, amongst other things. For instance, if you want to compare models, but also compare models between different scales, energy is a very universal constant to compare, variable to compare. Displacements will be U and the deformation gradient will be F. And in general, we try to use normal italic letters for scalars, bold lowercase letters for vectors, and higher order tensors will be bold capital letters. Again, like with terminology, these definitions may change from research area to research area, but this is a very common definition you may find very often. Starting with ductile damage, I would like to go into a bit more details here. So ductile damage itself describes a material degradation that's associated with plasticity. If we have a look on this specimen here, a tensile specimen that has been pulled from the left and the right side, we see that there has been some deformation here, some necking. So there has been plasticity, plastic remaining deformation. On a smaller scale, it's related to the formation, growth, and coalescence of voids, as we have also heard already in the previous chapters of this lecture. And classic approaches are found then for the very evolution for this growth of voids, such that for the model, we set up equations that predict how much void volume or area you may expect. Then voids do not only grow, they also nucleate, so they have to start somewhere. And the GPTN model is one of the most famous ones, probably based on Gerson's model, and also now adding the names of Tvergard and Needleman. And Lemaitre is one of the was one of the first who derived a phenomenological model in the spirit of continuum damage mechanics, that you may also still find in many other textbooks. Quasi-brittle damage then usually is associated without plastic deformation, so you see quite a straight crack here, but no necking, no plastic deformation inside. So that is understood to happen often in terms of cracks on the micro level and then on the macroscopic level. Especially when we talk about steel, we think here of low temperatures or higher numbers of cycles. So you see this straight line here. But if we go back here at low numbers of cycle or just for a simple tensile test at room temperature, we see necking, we see remaining plastic deformation here. While here on the macroscopic level, this is negligible for quasi-brittle damage. Classical approaches we find here is, again, Griffith that relates this damage type to the energy of the formation of new crack surfaces. And for the numerical implementation, we have an important contribution, for instance, in the form of phase field models for fracture. One basic concept to interpret damage in terms of mechanical variables is the effective stress concept. If we think that we are pulling a specimen from both sides, left and right, we may measure a force, F, in our testing device. And we relate that force to our stress sigma by a reference area A0 or A0. But if we understand damage as the formation here of small voids, then we see that the effective area that's bearing the stress here is not A0, the initial one, but we have to decrease that area by the damaged one, by AD. Of course, this is an oversimplified interpretation, but I think that helps a lot. There is not only one AD. This A may change over length, but if you want to assume, for simplicity right now, that we can describe something like an effective AD, we can reformulate this influence of this decreasing area. We can reformulate it to a D, to a damage value. Okay, so if we want to describe the effective stresses, these ones here, the blue one, we divide that side by A0 minus AD, and A0 minus divided by A0 will lead to 1, and AD divided by A0 will lead to D. So D will be in the range between 0, completely undamaged, and 1, a completely damaged state. The completely damaged state would be where we have an entire opening here through the entire area. Okay, and that's how these effective stresses scale. The interpretation is, for instance, that we have this decreasing or damaged area, and that can be reformulated into this damage variable D. So stresses are the ones that we can obtain here, and then sigma from microscopic measurements, for example, in your device. And again, I want to stress out that we have 3 pillars of continuum mechanics here: the experimental measurements, the theory, and the numerical implementation. And here we try to mainly develop the theory based on the observations and measurements. So we are measuring the force and the cross-sectional area F and A, for example, or A0 in this case. And we assume that strains are not modified here. So strains and effective strains, they are the same in this idea. And for 1D tension, so we are pulling on the left and on the right, we observe that sigma is 1 minus D times the effective stresses. And the effective stresses, these are the ones that we can relate actually to the other material properties. So the effective stresses, they behave or they relate to Young's modulus times the effective strains, because that is what we know from an undamaged material. We know for an undamaged material that we can determine the classical Young's modulus and the relationship between effective stresses, effective strains. And if we put these definitions inside here, we get at the end 1 minus D times the Young's modulus times epsilon. So the measured stresses here, sigma, for the damaged material is 1 minus D times the Young's modulus times the strains. You may ask yourself, okay, but what about the strains? Well, they may also fluctuate or change. And that brings us to the effective strain, to the effective strains here. And if we assume that the effective strains are the true strains, so the ones that are really observed here on a smaller scale level, if you want to, and we want to derive an effective macroscopic strain, we may see that there is some elongation in such a system. So this is a damage. This damage we observe, we pull from left and from the right side. And here, this one may open the damaged zone, and the strains then are distributed to the left and to the right. So we have strains in the bulk material, and we remove the strains that are related artificially to the crack here or to the damage opening. So we have the displacement jump U, and that's divided by L0. And this is what we do not want to take into account. That's not a strain that we can relate to a stress. That's the opening of the damage void, for example. We only want to relate stresses to the strain inside the bulk material. So we assume that damage increases linearly with the displacement jump, again here as an introduction to this course. So the larger this displacement jump, the more damage we have. So damage of 0 means no displacement jump, this will be closed. Damage of 1 will be that the displacement jump is the entire length here. So the stresses could, the strains could again be described in this approximation as 1 minus d times epsilon, the effective strains. The effective stresses here are not modified, because here we assume that we can relate the effective stresses directly to the effective strains. Okay. And for 1D tension, again pulling from left and right, we plug that in. Sigma is the effective strains just as well, so sigma tilde. This is E times the effective strains, and the effective strains are now substituted with the above equation, and we get the same result as before for the effective stresses. So we see there are two different interpretations available here: effective stresses, effective strains. They are, I think, a nice illustration of basic concepts of how we can understand damage. Heterogeneous material is, of course, a bit more complex, so that's why we use more sophisticated partial differential equations and numerical solutions for them. But this is already, I think, a nice way of relating the growth of damage in terms of nucleation, of growth. Maybe you can also think of coalescence afterwards if you think of the interface we have seen before, for example. So they can also coalesce. You can also have coalescence here, changing the area. But also in terms, the same applies to the strains. So you could have more displacement jumps, adding them up. And that gives us an understanding or an idea of how damage could evolve, could look like in these terms. Now I would like to highlight a challenge in the numerical implementation. If you had already a class on finite elements, you may be well aware of that, but I still want to explain it in a way that even people without a finite element background can follow this challenge here. So still consider the simulation now in a computer, because we have more sophisticated models of a tension test in a quasi-brittle specimen. Quasi-brittle because we will here focus only on the damage, and I do not want to go into more details on the plastic behavior. That would complicate it just unnecessarily. So let's put a small imperfection into the center element of this finite element discretization. So we have different elements here, and we are solving our equations in every element. And just to control where the damage starts, we put a small imperfection to the central one. We could also use another one here, but the center one is just for illustration. And now, in the context of the finite element simulations, we want to have accurate results, and we usually tend to have smaller and smaller mesh sizes to have a better approximation of the solution. Yeah? So each element might give us an approximative solution, like a linear function. And to get a better solution for the damage distribution, for instance, we had used smaller and smaller elements to get a finer resolution. The guiding questions could be, how will the force displacement curve of a simulation look like? Do we need to compare that to the experiments later on? What impact now does a different discretization have? What happens if I change the size of these elements? And do we observe mesh convergence for fine discretization? So in the best case, at least for elasticity, we quite often assume that if we get a finer and finer mesh, we would converge to a solution. If there is a unique solution, it exists, but in most linear elastic problems, that's typically the case for most practical problems you find in textbooks and lectures, okay, for linear elasticity. But now we have damage, so how will that be here in our case? And that brings me to a so-called problem of ill-posedness, because we see the following. If we use, for instance, 5 elements here, just 5 elements, and we are changing the size of the central one or making it finer, or can also adapt it. But here I just want to change the size. We see that the central element, as assumed here, is always damaging. So the integrity is dropping to 0 in this, and then in this case. So the left, the middle, and the right one. For a finer central element, we see this snap back behavior. For a medium one, we still see a small snap back, but this one and that one vanishes for a coarser central element. So from the coarse to the fine meshing, or a finer central element, we do not see a clear convergence here, and we see really drastically different force displacement curves. So really drastically different. And the results thus depend strongly on the mesh. But the mesh size should not affect the physical behavior. Not the damaged region, not the force response here. And that's because we used a local model. So we used a local model. And that means that our damage model just damaged the central element. And that element size dictated the area of the damage and the structural response. And therefore, there are a few solutions for regularization of that ill-posed problem. These solutions aim at fixing the size or the width of the damage zone. So before we were changing the damage zone with the element size, and now we want to have it independent of the discretization, so independent of the mesh size. And the 3 ideas are the so-called fracture energy concept, the viscous regularization, and the gradient regularization. As an example, we use an L shape that's fixed at the bottom, and we pull on the side. And we see here the damage zone that's evolving for the 3 different methods. The first one is the fracture energy concept. It aims at modifying the mesh to match the physics. So it's not really a true regularization, but an adaptation of the numerical settings. So knowing your mesh and knowing your physics, you can try to match both, to adjust all the numerical settings such that they match the physics. But then you must only use that single element size over and over again, or element type just as well. So it's fast for a single problem once it's calibrated, because you're just adjusting the numerical settings according to your mesh. But it can be a cumbersome calibration for each new problem. For another problem where the crack or the damage zone may evolve in another direction, or if you have another geometry, another load type, you need to do that again, because it's usually not a very transferable approach. It's limited by the mesh resolution and the shape, so you can have a bias in the crack or damage shape. And the ill-postedness of the actual partial differential equations is not healed. So you still have an ill-post problem there. The point is that you just know that your numerical settings will work for that very mesh. The advantage is if you use that mesh size again and again, because you do a parameter study in industry and you're sure you will not change your settings for the next 5 or 10 years, you may want to go for it, but still from a scientific point of view, that's not a reliable option. Another option would be the viscous regularization. So it puts an inherent viscosity, and viscosity is usually related to velocities or velocity gradients. So you have another time scale. And the time scale that transfers via viscosity to this length scale or to this width of the damage zone. But that's not a physical one. That's an artificial setting of this width. And more importantly, we have heterogeneous strain rates in our problems usually, and therefore we have a heterogeneous damage development. So you see that this is not a constant width of the damage zone, and this can be a problem then for the viscosity approach. The gradient regularization then adds a gradient term to the energy typically, so you have a higher order derivative. You may think of strains that are the spatial derivative of displacements. You can add a higher order derivative there, or you would add, like in this case, at the gradient of the damage. So the whole evolution does not only depend on the damage, but on the gradient of the damage. In other words, it depends on how the damage changes in space here. And this means you are controlling this change of damage in space by this gradient approach, and therefore the width of the damage zone. It has the highest accuracy here, and also in this example of this L shape, it has negligible or no interference with the basic model. So you're not changing or adapting the mesh here. You can change another mesh. You don't introduce viscosity that's unphysical. It's probably the most beneficial all-purpose framework. It comes at the cost of higher computational effort, so it's more costly in these terms, and you can have an interaction with the curvature of that damage evolution, but that's what I would assume in these problems still negligible compared to the interference that the viscous regularization had, for example. And that brings us now to the more sophisticated damage models that I would like to have a look at with you with a few more details. So let's start with the microscopic scale and see how examples and developments are made in the recent years. Have been made in the recent years. So starting from a forming process, this forming process could be rolling, it could be forward rod extrusion. It could be anything else of a forming process you may think of, or bending, for example. There is a microstructure involved in your material typically. And for that reason, you find numerical models that capture that microstructure and that have damage then accounted for at the grain boundaries. And apart from that, because you can have an interface dominated damage between these grains, at least the interfaces, and also inside these grains. And these grains are sometimes assumed to be to show plasticity, sometimes also a damage like in martensite cracking. So you want to combine the behavior not only of the bulk phase, but also of the interfaces. And under different loading paths, then you can get a different mechanical response. And for such microscopic damage models, it's quite often almost impossible or practically impossible to perform a simulation of the entire body. So you find very often calculations or examples where you have a so-called representative volume element, an RVE, where you no like stresses or strains that are applied to different points of your formed part, and then you use these loading paths and only compute them for the material point or for this representative volume element. So you're only performing single elements, not the entire geometry, if it would be too costly otherwise. All right, so this is the idea of a microscopic model. And one approach here that I would like to show you here is the interaction between crystal plasticity and the decohesion at the grain boundaries. Again, you need to take into account the bulk, like the grains themselves, but also their interaction. So this representative volume element is a polar crystal, like you see here. And inside these crystals, single crystals, you have a physical response. You can have plasticity. So you have slip planes, for instance, and they are sliding. They are computing the different directions with the crystal plasticity model. So the yield function in multiple possible directions. And this is typically not a well-defined problem. So you can have an algorithmic formulation to find these slip planes then for different yield functions. And for the interface, you then have another energy for the interface where you have a displacement jump, for instance, for opening interfaces, and for the deformation gradient of that interface, and with internal variables like the damage, for example, in normal or tangential direction. So you have again damage variable not only in the bulk but also at the interface with different directions here between the grains, how they interact, and with an extended balance of linear momentum here. Please take into account that you have two grains attached to an interface. So the classical balance of linear momentum divergence of the stress is not only zero, but it couples the stresses from both sides, so from both grains that are neighbors of these interfaces. And here again, as a short reminder for the crystal plasticity model, this crystal plasticity model here has of course, a structure of that crystal, so you can have multiple yield functions and slip planes. If you are familiar with classical plasticity, you would have only one yield condition here, but here you have multiple ones. And just to give an example how the result looks like, you can have here the plasticity within the grains. You can compute the equivalent plastic strains shown here. So some grains undergo plastic deformations, some do not, or not yet. And then you have the decohesion at grain boundaries, where you have the distribution of damage, for example, localized here inside this RVE. And then you can investigate that for different strains and the resulting stresses, for example, so epsilon and P here on the macroscopic level, so of the overall volume, and that gives the potential to understand what mechanisms are active under specific loads in my material, and also is there a possibility to improve that, so redesign it, for instance, or also improve some geometric features of the composition.
While microscopic approaches offer detailed insights into the material behavior, as we discussed in the other section, they can be computationally expensive and sometimes impractical for large-scale simulations. This is where macroscopic models come into play. These representations capture the essential mechanical, thermal, electrical behavior of the materials at a larger stage. For motivation, I would like to discuss the first figure. Here we have a notch tensile DP800 steel specimen. First of all, we have load displacement curve. During tensile loading, the material first undergoes elastic deformation, and later plastic deformation starts. And this results in a nonlinear response in the curve. At one point, the force reaches the maximum value, and after that, necking starts till the catastrophic fracture point, as we see at the end. In our models, we would like to, of course, take into all this information regarding the material response into account. And taking this as a motivation point, I would like to introduce continuum damage mechanics. Continuum damage mechanics denote a collection of approaches and models focusing on the simulation of the degradation of the material, degradation phenomena. In these approaches, specific microstructural features and their evolution are not resolved. Rather, the effect of the underlying microstructure on the material response is modeled. What can be these different microstructural features? One can think voids, grains, grain boundaries, inclusions, microcracks, and all the others. And in these approaches, different damage mechanisms such as microcracks, cracks along grain boundaries, growth of voids, rupture, and decohesion are cumulatively taken into account. For example, we can employ phenomenological models, which describe the behavior of a material based on macroscopic observations, but really without considering the underlying mechanism. To model ductile damage, in these models, it is common to introduce a scalar-valued damage variable d, or this can be also tensorial. In Lemaitre type models, often referred as 1-d models, damage is modeled as the degradation of the elasticity and the plasticity-related quantities. As we discussed in another section, due to the degradation and the softening effects, the underlying mathematical problem is not well posed. And this all results in mesh dependency of the finite element-based simulations. In order to overcome this problem, different techniques can be used, such as non-local damage models, gradient-enhanced or macromorphic approaches, and rate-dependent formulations for the damage evolution. Here, for an example, a gradient-enhanced ductile damage model in finite strains with algorithmic strain measures is introduced. So in this model, first a non-local damage variable is introduced, and the gradient enhancement of the model is achieved by incorporating the gradient of this non-local damage variable. Additionally, we have also a local scalar damage variable, d. And due to the scalar nature of this damage variable, here we have isotropic damage. And here for the local part of the energy, we have the isochoric and volumetric contributions. And also here we can see the so-called damage functions, which degrade the effective elastic properties of the material for increasing values of the local damage variable. This function f takes values between 0 and 1. So we can think that when there is no damage, the damage function is 1, so that the stiffness of the material is initial. However, when the damage starts to accumulate, damage function results in degradation of the stiffness. This described ductile damage model now can be employed to predict the behavior of DP800 steel, for example, as a real-life example. For this purpose, parameter identification is necessary, which is, at the end of the day, a numerical optimization scheme. An optimization algorithm must be carried out to determine the optimal parameters in terms of an objective function, which evaluates how well the simulation results and the experimental data match based on the least scarce criterion. We can see this procedure from the top figures, and in the last figure, experimental data and simulation are in a good agreement after identifying the real material parameters. As we discussed before, in order to overcome the mesh dependency, we need regularization techniques. And these concepts actually can be really important for damage and plasticity. The first figure explains the phenomena rather nicely. Here in the first figure, we have gradient-enhanced damage formulation in order to have mesh-independent results for the damage-related fields. However, we have local plasticity model, such that we don't have an additional non-local field variable for plasticity. As we see from the first figure, this results in rather mesh-dependent results, and we can see here the localized region. But in the second figure, now we see non-localization. And this is due to the fact that now we have a gradient-enhanced plasticity formulation used. And now, another important aspect of this model is related to the tensorial damage variable concept. Before, for the isotropic damage evaluation, a scalar damage variable is introduced. However, in order to include deformation-induced evolution of the anisotropic damage, a damage tensor is needed. Different effective driving forces for both plasticity and damage are derived in a so-called two-surface formulation here. And what is two-surface formulation? Which considers two admissible domains, one related to the plastic flow and one related to the damage evolution. Till this point, we have discussed different approaches to model damage in different scales. Right now, we will discuss another important concept, which is multi-scale approaches. A multi-scale approach, in a general way, is a way of studying a system by considering its behavior at multiple levels, or size, or detail. It is particularly useful when a system exhibits important features across a wide range of scales. A multi-scale approach in mechanics bridges the gap between the different size scales. It involves, first of all, identifying relevant scales. This involves understanding which scales are important for the phenomena being studied. Second one, we have to develop models at the macro scale. So we need microscale models that represent the behavior of the system at the micro scale. And of course, these models can be calibrated, for example, by the experimental data that represents the realistic response. And the last of all, we need to link these scales because we have our micro scale and we have our macro scale, and we need a link between, or we need a bridge between. For the last step, we need to link these two scales by averaging theorems, homogenization techniques. These techniques translate the information from the micromechanical models to the macroscopic level in an effective way, allowing us to predict the overall mechanical response or the electrical response of the material. So here I would like to discuss electromechanical setting for electrical conductors. Here we have two scales. One being macroscale that includes microstructural features such as voids, grain boundaries, microcracks, inclusions. And the other one is macroscale, which we can think it's a tensile sample made from DP800 steel. We would like to have electrical resistance measurements. Here the idea is we would like to interpret the electrical conductivity or the resistivity value at the macroscale as a fingerprint or an indicator of the underlying macrostructure. In order to understand the effect of damage on resistance measurements or resistivity values, single-scale phenomenological models can be also, that we have already discussed in this section before, can be also employed. However, these models only mimic the effective macroscopic material response, so information regarding the macroscale is not really resolved. And it relies on some set of assumptions. However, for the multi-scale approach, we can resolve the macroscale with regards to the material microstructure geometry and individual macroscale material models. And by means of homogenization procedure, we can obtain the effective response of the macroscale in the form of stiffness, conductivity, resistivity, and so on, and use these effective properties in our macroscale problems, in our higher scale problems. Here, this example shows electrical problem setting, only electrical problem setting. In the bulk, we have a linear elastic response is assumed or proposed, such that the electric current density J and the electric field E is related via conductivity tensor. Here, conductivity tensor is also assumed isotropic. We can see that we have two different microstructures. Let's try to understand the first example. The initial conductivity of the bulk is assumed to be kappa here. So we have isotropic kappa. First of all, when there is a pore present, we would assume a reduction in effective conductivity, since here pores will act as an interruption for the electric flow. Second thing we are observing and we are expecting here is when the pore is circular, we expect to see an isotropic response. We expect same reduction in conductivity in every direction. due to the geometry of the pore, which is a circle here. So when we check the first effective conductivity tensor, we see that we have approximately 25% reduction in every direction in 1,1 and 2,2 or XX and YY. However, the second microstructure is ellipse now, and we expect to see the effect of this geometry on the macroscopic effective conductivity tensor. Here we see that the reduction in the 2 direction or Y direction is significantly larger than the X direction. I mean, we see a significantly anisotropic response here. That is also something we can observe from the figure. When the current flows in Y direction, it encounters a large interruption. And when it flows in the X direction, comparatively, the interruption is less. This example summarizes the idea of using electrical resistivity or conductivity as a damage indicator, because we are seeing, due to the nature of the voids in the microscale, we are observing different conductivity values on macroscopic measurements.
And talking about performance, of course, if you have a damaged component, you want to know more about the lifetime, about the performance until there will be really failure. And therefore, damage can evolve even more, for example, after some forming process, by fluctuating stresses and strains. And for that reason, I would like to distinguish here the low cycle fatigue and the high cycle fatigue behavior. Low cycle fatigue is typically understood as the nucleation of microcavities, of course, by plastic deformation. So we have these voids that grow, and they may coalesce to macro cracks for this ductile damage process. There is not always a clear cut that depends for the number of cycles here. We will see, for example, experiments about 100 cycles. That of course depends. The transition is smooth between low and high cycle fatigue and depends also on the material of interest. If you want to model ductile damage at the macro scale for this fatigue problems, we first of all assume a fictitious undamaged state and a damaged state. So you have strains here, for example, and some internal variables. For example, also the energy description here. And for the damaged state, then you would have some voids here or micro cracks, typically voids for ductile damage. And it's a bit similar to what we have talked about before, to the effective stress and effective strain concepts, but here more on a more sophisticated level, in the sense that we have now a complete framework in terms of energy, in terms of stresses and strain as tensors in all directions, with hardening due to the plasticity. So again, what you may want to start with is a Helmholtz energy that depends on the elastic energy. That depends on the strains, actually on the elastic strains. So we need information on the total strains and the plastic ones to get back to the elastic strains. And we need to know the integrity B, which is, for instance, 1 minus damage. And knowing damage then, and knowing the elastic strains, we can compute the elastic energy there. The damage, again, to emphasize that, can lower the elastic moduli, so Young's modulus, bulk modulus, P-wave modulus, and so on. And we have plasticity added here because we are talking about low cycle fatigue, so we have plasticity involved still, where we have some kinematic or isotropic hardening values, and also damage or integrity that's affecting the plastic potential. And the plastic potential, sorry, a G here, that contains the flow rule together with the interactions between alpha and B here, between the damage values. So a modification of this initial yield function. the most important contribution or addition here actually with respect to the damage is gradient contribution. So again, talking about damage models, this is a local approach here. This is more sophisticated and adapted plasticity description, but this gradient contribution now uses a different field for the integrity here, phi, and then adds a gradient of this phi variable. This is the gradient regularization you see here. You see the length scale LB, and this will dictate or gives us control over the width of the damage zone, for example, the damage transition zone. And such a model can then be used, focusing on integrity, to perform some predictions of the cyclic loading. We start the video here. So we have tension compression here again, and the damage zones here evolving. So you see the integrity tensor decreasing, this BZZ, so in actual direction. And here you see a load that's increasing. Displacement is also increasing, and we are going back and load and displacement, and back and forth, and so on. You might see here some change of the slopes. So you see one slope here from the start, and the slopes are also decreasing because the elastic moduli are decreasing at the end. Also, you see that the maximum load here from the experiment can be transferred to a maximum stress, and this means that you also have an influence of damage that evolves during the cycles on the plastic limit here, on the limit. And even more so, in addition to the damage, we have here shown an damage initiation control parameter that tells us, based on the plastic energy, so you see plastic energy here, you see a further function for the adaptation that depends here on the maximum equivalent plastic strain, when the damage is allowed to initiate. So we control, or we observe the developing plastic deformation. So we see there is some plastic deformation during every cycle. We then choose the most relevant parameters, put that into these functions here, to the potential into F. By that, we compute the initial damage initiation parameter, and that then allows damage to evolve here is B. Okay, and that is how you can relate also complex damage evolution. For example, anisotropic damage evolution, different damage in different directions. You can relate that to the plastic deformation by these types of equations. And I think these equations now are the most relevant ones when you want to deal with damage here. Not as a post-processing step that you may find in some very simple commercial software packages, but this is really damage affecting the other physical mechanisms on the fly here. This is not a simple post-processing, but we are really, with these creations, you can change your physics during the deformation, and that's very important to know. And it's important to know that, for example, if you want to do optimization, optimization can be understood in different ways. Here we want to improve a structure, for instance. It depends on objective function that's subject to some constraints. And you find many design studies that assume that you have only elastic behavior that reduces your computation time. Implementation is simple here, but here we want to show or see how damage may change the whole picture if you do not only assume elasticity but also damage effects actually. So let's assume here we have some ductile damage effects, and how we can, let's see how that can improve our prediction. So the damage, the general idea is we want to optimize our whole process with respect to the accumulated damage. So you may have damage here in this example when you are pulling this geometry at top and bottom. You see some necking here, and you want to adapt the shape to reduce damage as possible. And what you see here is we have an early damage localization. So we meet that objective to reduce damage by confining the damage to a small area. But still, it leads to preemptive failure here. So another approach you can use is to include a global damage constraint, the same objective function, but we want to prevent optimization-induced early localization. This means we use another shape here, pulling on top and bottom, but one that controls damage optimization in the sense that damage is spread over a larger area. So it's not localized to a small area anymore. That may be more risky for your application, but we want to control the damage optimization in the sense that we have a lower maximum damage spike here. And then we also have a longer durability regarding the damage. Okay, so damage is there. You cannot always avoid damage. That's not what you can do. But you may want to modify your geometry or your process in the sense that you can control damage. Even not avoiding it, you can control it. And by spreading it over a larger area here, instead of having a localized peak, could show you how you can reach longer durability. Another option would be, or another comparison I would like to show you is the compliance optimization, where we compare really now the conventional elastic optimization, where damage is only computed in a post-processing step, and another one where you really have a coupled optimization, where damage is really calculated during the simulation. Now, on the left side, that's maybe a very standard, but not very accurate approach, where you compute the elastic problem, and then afterwards you compute damage that would have been evolved. On the right side, the more sophisticated approach based on the equations you have seen earlier, where where the deformation updates the damage variable, and therefore always updates also the elastic moduli and the degradation, okay, during the simulation. Both have the same mass or volume, and what we see is that the purely elastic computation with the damage post-processing and the elastic plus damage control have a very similar behavior at the beginning. So in the elastic regime, then you see plasticity here. That's also still quite similar. But then after the critical force here, or the maximum force regime here, you see that both start to deviate. Okay. And this means that the coupled one, the blue line here, allows still a much larger force in the critical area where your component may fail. So this is the safe area here in the beginning. The elastic one, we have some onset of plasticity. That's where you still can sustain more force. But in case you really get into trouble during operation, that's when you exceed this force point here. Well, that's the problem. That's when things get worse. And that's where we see where the elastic plus damage control here helps to yield geometry with the same mass and same volume with a much more sustainable force. Okay, so this is why it's important to consider damage already during the simulation and not only as a post-processing step. So we have a higher damage-resistant behavior, and we have larger safety margins towards damage here when we take into account damage during the simulation already. This brings me to the references, where we have put some historic articles and books. We have put here some some general books. We have put some novel articles, depending on your background. If you want to have a very new article or if you have a journal book, you may want to go back to the slides and check the names and years. And here you will see these references again listed. And you see also, I think, a nice overview of a nice collaboration of different groups that focus really on damage control via modeling and the numerical implementation. And they continue here. You also see how they developed during the recent years. And as always, there's still much to go for in this research area. Let me please also thank my colleagues, again, that helped to create these slides. And I hope that you got a first insight into damage modeling and its numerical implementation. Thank you very much.